Welcome to video 1 of the Marching Cubes and Minimal Surfaces series. This is the second video in this series, but the first in which we actually go into Grasshopper and start writing scripts. If you haven't watched video 0 already, I think it will be helpful to see that first, so you might consider jumping over to that video. It'll make what we're going to do here much easier to understand. This is an advanced Grasshopper tutorial, kind of at the easier end of advanced, I think. So we'll go kind of fast through some of it, but if you're new, maybe you're up for it. By all means, follow along, and I'll try to explain as much as I can while still moving pretty quickly. And one more note before we start. I recorded most of this kind of a long time ago, a while ago relative to this last sweep as I piece everything together. And so, hopefully not surprisingly, I have more experience now with Grasshopper and coding than I did then when I first recorded it. I'm always learning, but everything in this tutorial is still perfectly fine. But as I go through it again, if I come across anything that I would do differently now, I'll insert a clip explaining what I might do a little differently. I'll walk through a new way to do it or a different way to do it, and I'll explain why. And also, Rhino 8 was released after I recorded this. That doesn't make any difference for most of this, but the scripting component in Rhino 8 is a little different than the one in Rhino 7. And we do write a lot of code in this tutorial. So in case anyone watching this is new to C#, I've inserted clips that explain how the scripts would look inside Rhino 8 scripting components. And I walk through how to do it in Rhino 8 as well as in Rhino 7. Anyway, in this tutorial, we're going to go through the most basic version of the Marching Cubes algorithm, and we're going to build everything from scratch. I think this is a beneficial thing to do for a number of reasons. First, it's a great way to understand some new techniques or approaches in 3D modeling. By building it from the bottom up, you'll learn some valuable skills if you're a computational designer. Second, after you're finished, you'll have a component that you've built from the ground up, so you'll have a much better understanding on how to fix things when they aren't working right, or how to adapt it to a specific use case. This is why a lot of the time I'll choose to make my own components rather than searching for something that someone else has made. Don't get me wrong, Food for Rhino is wonderful, and I appreciate so much the work people do to populate it with great components. It's also great when people share libraries on GitHub, and with these you can actually see how everything works, kind of like when you make your own components, or at least you can see how a lot of it works. And so sharing these things, sharing what we build and sharing what we learn is always awesome, and it really makes everything possible. But I guess what I just want to say is that when you have a component that you created, it's easy to fix or modify. It's easy to adapt because you know exactly how everything was put together. So we're going to build the basic version of this algorithm from scratch. There are more advanced versions out there. This is not a new algorithm. It was first put out there in 1987. And here's a timeline, a very incomplete timeline of some of the updates and improvements to the algorithm. A lot of people have worked on and contributed to versions of this algorithm. So if everything were up here, it would be very long, but just in case you're curious, you can look into some of these. And of course, there are many more resources at nuLUCA Pavilion's website. If you're not already there, there's a link to it below. Marching Cubes was first used for medical imaging, and later its potential became very obvious for use in things like computer graphics and computer games. It's very helpful for us in 3D modeling. If you were looking to make your own custom component in Grasshopper, you might want to go straight for something like the transvoxel algorithm. But if you're just looking to implement the Marching Cubes algorithm in Grasshopper and get some usefulness out of it more quickly, or in our case, if you're looking to use Grasshopper as a way to internalize this logic, as a way to understand what's really going on, then the basic algorithm gives us all that we need. It gives us something great to work with. Also, if you were looking to create your own custom component, you would probably just copy and paste a lookup table. But again, if you were creating this algorithm in Grasshopper anyway, I think it's actually faster to just make our own lookup table rather than trying to deconstruct and reconstruct a table that we find online. And that all being said, now that this basic tutorial for the Marching Cubes algorithm already exists, it might be worthwhile in the future to make another tutorial in which we follow up on this one and create our own custom component, one that exists up here with all of these components. And for that, we would use a more sophisticated version of the algorithm. So maybe I'll do that in the not too distant future. But right now, let's do a quick overview of the basic Marching Cubes algorithm. I'll use a finished script of the script we're about to write for this tutorial, just to demonstrate the basics. So don't worry that obviously you don't have any of this on your Grasshopper canvas. You don't need it. We're going to build it in the next few videos coming up. I'm just going to use it to describe how the Marching Cubes algorithm works. You can think of this algorithm like this. You have a bunch of points in space, And let's pretend we know only one thing about each of these points. We know whether or not they're inside of or outside of a volume. Either yes, this point is inside the volume, like inside the material of a wall, inside a hockey puck, inside a piece of furniture. Whatever volume you're trying to model, is this point inside of it or is it outside of it? With just this information, we can make an approximate meshed surface that encloses whatever volume we're trying to model. And then we can fine-tune that mesh or get a much better approximation if we know about how far or exactly how far from the surface of that volume each point is. But we'll get to that a little later. First, just know that each of these points is either a yes or a no. So we can visualize that. I'll just put some mesh spheres at each of these points to visualize this, or maybe some dots. Let's make these a little smaller. And let's vary the color on whether or not they're inside or outside of a volume that we're trying to model. And that information is going to come from this evaluate function component. We'll get to this later too, but just for now, I'm going to separate the positives from the negatives. So I'm going to say smaller than 0. And let's get a merge component. I'm going to put two colors together. We'll have a gray and a dark gray or black. List item. And these can be our colors. So you can see right now about half of them are one color and about half are another. That means that the surface is kind of splitting this space in two. So what the Marching Cubes algorithm does to make this much simpler is it only focuses on one little cube at a time. So I'm going to disable all of this. We don't need it for now. But let's keep it around just for a minute. And let's zoom in on one cube. So let's look at this cube right here. Just one cube, any cube really. And we'll turn all of this off. So instead of trying to think about all the cubes at once, we just look at one cube, and then luckily for us, computers are really good at doing a lot of things really fast. So as long as we know what to do with just one cube, we can make a mesh for the entire space. So what do we do for just one cube? We have 8 points, and we will have a Boolean value for each one of these points. Each one of these corners of the cube is going to be either a yes or a no. Is it inside the volume or is it outside the volume? So right now I'm just going to color code these 8 vertices like we did with all of the points just a minute ago. I'm going to take these and just change these a little bit. This probably won't make sense until you've gone through the tutorial what exactly I'm doing right now. Okay, so if all 8 corners are the same, if all 8 corners are either yes or no, then that means we're either inside completely or outside completely of whatever volume we're modeling, and so no surface goes through this cube, so we don't need to put any mesh inside of this cube. But if one corner is on the outside while the rest are on the inside, like this for example, you can see this corner switch to light gray and the others are dark gray. Then the surface is cutting through this cube a little bit, and we would put one mesh here between the volume interior and the open space around it. This is where the surface would be. Let's get a face normals component and a vector display and a multiplication just to adjust the size of our normal a little bit here. So if you're familiar with meshes, you know that the normal is important in things like computer graphics because it's telling you which side is facing out. It's a little less important in Grasshopper, but it still is important. We want all of our faces to face in the same direction. We want all of our meshes to be, all mesh faces to be oriented in the same direction. Normals face out. The normal vector faces out. So the normal here is facing into the open space, the space where an observer would be, where you can see the object. We have all the dark gray corners in the open space, and the light gray corner is enclosed inside the object where we wouldn't be able to see it. So this is what the mesh would look like if there's just one dot on the inside of the volume. And then we can keep going through. What if 2 dots are on the inside? Then we would have a mesh that looks like this. And in this case, we have 3 dots that are inside the volume, and all of these dots are outside of the volume, and we would put a mesh like this in this case. And we can scroll through all of the possible scenarios. This is what I mean when I say a lookup table. We're going to be making this so that we can quickly know exactly what the mesh will look like at every cube in space. And in total, there are 256 different possibilities because there are 8 corners to this cube. And each corner can either be inside or outside. That means there are 2 possibilities for each corner. So 2 times 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 2, or 2 to the 8th power, is 256. Just like there are 256 possible values for RGB, red, green, blue, because 1 byte, BYTE, is allocated to each color, and 1 byte is equal to 8 bits. 1 bit is just a 0 or a 1. So you can have 2 possible values, and 2 to the 8th is 256. So right now this number slider goes from 0 to 255. And it contains all of the meshes that we'll need for the marching cubes algorithm. And it sounds very tedious to have to make these 256 different combinations and put them into a component. But luckily, again, for us, is that we actually only need 14 different meshes. So if we go back to this one, number 1, the first one in here that actually contains a mesh, we can see that this is the exact same thing as this. It's just rotated. And so we can simplify this down to 14 different possibilities and then rotate and mirror these in all kinds of different ways. And that'll cover all 256 different combinations. So these are actually the 14 cases that we need, along with the null case. And the graphics shown here are straight from Lorenzon's original 1987 paper. I mentioned briefly that there are some more sophisticated versions of this algorithm. And that's because with the 14 that we're going to use today, there are some ambiguous cases. There are some cases that even if you know all the Boolean values for these 8 corners of the cube, there's not just one mesh that will satisfy that. There are a few different possibilities. And so there's ways to kind of look a little bit deeper, get a little bit higher resolution, and figure out what is actually going on at that point in the surface. But again, we don't need to worry about that today. This algorithm is going to work great for us, and with the tools in Grasshopper, we can fix any flaws that come out, if they do come out. And so maybe this is surprising to you, or maybe you can intuit it already, but all we need to do is just the same thing for every single cube in the whole space. So if we zoom out, we can hide all of this. Let's show these points again. So if we just run that algorithm for all of the different cubes, we'll get a surface that looks like this. And it separates these 2 sides. And again, like I mentioned earlier, it's going to be a little bit jagged at first. But when we incorporate actually how far each point is from the surface, when we incorporate the actual distances, we go a little bit further than just Boolean yes or no's. Then we can refine the mesh a little bit more and get something smoother that looks like this. And this is a pretty simple set of points we're using to make this relatively simple surface. We can put in point data from much more complicated environments. Also, we can refine these meshes even more. So now that we have a broad overview, let's start to make all of these meshes. Let's make this lookup table. Let's start by making the corners of a cube. We'll do it the quick and dirty way. Let's get a construct point component and a slider from 0 to 1. We'll need 8 of these, so let me copy this 4 times and then 4 more times. So now we have 8 construct point components, and these points are at 0, 0, 0. We'll put point 2 at 1, 0, 0, or point 1, sorry, this will be point 0, 1, 2, 3, and then 4, 5, 6, 7 on the top. So that's point 2. Point 3 will go up 1 by y also, so that's 3. Point 4 will be just y. And then all of these are going to be up 1 on the z-axis. And this one's going to stay at 0, 0, 1. This one will be 1, 0, 1. This one will be 1, 1, 1. And this one will be 0, 1, 1. Okay, let's merge all of these. Put these all in a point component. Let's call this cube points.
And I'm going to internalize this data, and we can just delete this now. To visualize the cube, let's just make a line between the points that make edges for the cube. There will be 12 lines. Let's get a line component, and let's get 12 of them. So we got 4, 8, 12, and I'm going to leave that cube component here. I'm just going to copy it just so I know where to grab it every time. It's right up there. And I'm going to get a list item and pull out every point. So we have a line from 0 to 1, from 1 to 2, from 2 to 3, 3 to 4, not 3 to 4, sorry, 3 to 0. I'm going to get rid of this grid so this is easier to see. And then we have lines 4, 5, 5, 6, 6, 7, and 7, 4. Then we have lines 0, 4, 1, 5, 2, 6, and 3, 7. So I'm going to merge all these also. Put them all in curve component. Call this cube curves. I'll internalize this data, and then we can get rid of all of this. This can just be just a white color. And let's just custom preview this. Get a color swatch. Make this light gray. And for the points, let's number them because we're going to have to pay close attention to the numbers throughout this whole process. So I'm going to get a point list. What's the default size here? That'll do. Then of course we need our mesh points, which are going to be at the center of each of these. The mesh vertices will be at the center of each of these edges, the edges of the cubes, the cube anyway. So let's just get curve middle and a point component. We'll call this vertices. And I'm going to internalize this data also and delete this. So this will also be important. Make it yellow. I'm going to hide this and bring another one down here. So we have the vertice numbers 0 through 3, 4 through 7, and 8 through 11 are in the middle. It doesn't really matter as long as we remember where they are. Okay, and now for the tedious part.
Okay, it's me from the future. It's actually not that bad. It's not that tedious, but I guess it is kind of tedious. Basically what we're going to do next is make 14 meshes using C#. We're just going to write out the instructions to make 14 different meshes. But if you're a nuLUCA Pavilion member, you don't have to write all this out if you don't want to. All the scripts are available for download. If you're a member, or even if you're not a member, the code is also available to copy and paste for these meshes at the Pavilion website also. So you can skip most of this tedious part if you want to just copy and paste the code from the website. And if you're watching this on YouTube, there's a link below to that. That code is just describing the 14 different meshes and their associated Boolean patterns coming from the inside or outside cube corners, the yes or no Boolean cube corners. So back in the tutorial, here I'm just talking about the 2 to the 8th thing. If we have 8 Boolean slots, 8 yes or no values, there are 256 combinations. So eventually we'll get to 256, or 254 actually, not counting the 2 null cases, the all yeses and the all nos. But we only ever have to write 14 meshes because we're going to rotate and flip them to fill in the rest. Also, as I mentioned earlier, there are some differences between the Rhino 7 and Rhino 8 scripting components. The differences in the code we actually write is small to non-existent though, but since this is the first video, I walked through this with the Rhino 8 component at the end of this video as well. So if you'd like to skip directly ahead to the Rhino 8 part, you won't miss anything if you go to minute 27 or so. There, I'm just doing the exact same thing I'm about to do here, except I'm going to do it in the Rhino 8 scripting component. In future videos, I'll just show the code inside the Rhino 8 component so that we can keep the lengths of the video a little bit shorter, and since it's a bit overkill to walk through everything twice, since it's basically the same. But if I update the code at all, or if we need to convert an input to a list or something like that, I'll call that out. So let's get a C# component to make these meshes and their associated Boolean patterns. So I'm just going to type C#. So the input here is just going to be our mesh vertices, the midpoints from our lines. So I'm just going to call this input vertices.
And this is going to be, we need list access, and these are 0.3D. So let's plug these vertices in. And we'll have two outputs. We'll have our mesh tree, and we'll have our Boolean patterns. And so these patterns are going to be 8 digits long, 0, 1, 0, 1, 1, and so forth. And each Boolean pattern is associated with a different mesh. So inside our C# component, let's make a data tree of meshes. Let's call it mtree equals new data tree. And then let's make a data tree of integers. We'll call this iTree. And for the integer tree, instead of just writing one integer that would be like 1, 0, 1, 1, and so forth, we need to put them in a list. So the first item in the list might be 0, then 1, then 0, and so forth. So there's going to be 8 items in each of these lists. And the reason we're doing this is so that we can later organize our meshes in branches. And the branch pathways are going to be zeros and ones. So the first path is either going to be 0 and then or 1. And then the next path beyond each of those will be 0 or 1 and so forth. And that'll be a quick way to get to each mesh rather than asking C# to look up to match numbers, to match, say, 56 to 56.
I'm not sure if under the hood this is actually any faster, but it's still a convenient way for us to organize the meshes and to find them later when we're calling them. So again, there will be a lot of repetition here. I'll talk through the first mesh in this video, and then in the next video we'll fly through the other 13. But if you want to copy the code, you can go to the nuLUCA Pavilion website. The link is below if you're not already there. If you'd rather copy and paste, and I imagine you'd rather. So we're just going to repeat this process 14 different times, essentially. So let's get a new mesh, M0, new mesh. And we'll need a new GH path each time because we're going to put each of these meshes in its own branch. So new, and this one is going to be 0. And I forgot to give this a name. We'll just call it path 0. And then let's do a for each. So for each vertex in vertices. And this is a 0.3D vertex in vertices. M0 dot add, M0 dot vertices dot add vertex. So that way we get each of the vertice points 1 through or 0 through 11 in that order as vertices for this first mesh. And then let's add the faces. So M0 dot faces dot add face. And this first one is going to be 083. And the next step is just to add this mesh to our mesh tree. So mtree dot add. We're going to add M0 and path 0. So first we put the data that we want to add, and then we specify the path that we want it. So that's our first mesh. Now we need to add the Boolean path for this mesh, and we'll add that into our iTree. So each time I'm going to separate each mesh with one of these. So the mesh and the Boolean pattern will be together between a couple of slashes. So let's make the GH path for our integer tree.
and we'll call it iPath0 equals new GH path, and that will be 0 also. Let's get one more space between these, and then we'll just do this manually. We'll grab iTree.add, and the first Boolean in this list is going to be 0, and we're adding it to this path. And I'll split it into 4 so it's easier to see. So we have 0 for this path, and then 1, 1, 1, and then all of these are 1s. And that's it for the first one. Let's go ahead and bring these out. What did I call these? Mesh tree and bool patterns? Okay. So mesh tree equals mtree, and bool patterns equals iTree. Let's see if this works. Does not. Okay, type but use like a variable 58, 59. It's because I forgot to write new in both of these spots. Okay, now it works. And so this one, if you remember, it was 0 and then all the rest were 1s. So let's get a face normal, and let's see which way this is pointed. See which way the normal's pointing. So vector display. This is our vector. We'll center it here. So it's pointing towards the 0, which is good. We did it in the right order, because all of the 1s will pretend are solids and all of the 0s are open space. And so this face is pointed towards the open space as it should. From here on out though, we'll need to specify a tree branch, and let's get a construct path, which I probably don't need, but okay. 0 through 14. Oh, I'll keep that. So now if we want to check any of these, we can do that.
Okay, so that's it for this video. Unless you would like to see how it's done in Rhino 8, it's really not all that different, but I can show you where the differences are. So if you did follow along and have already built the first mesh in our scripting component, then go ahead and skip to the next video. Otherwise, if you want to see how it's done in Rhino 8, stay tuned to this one. Actually, the script is exactly the same. So let's get a scripting component. So in Rhino 7 you could write C#, but in Rhino 8 you need to write script. And then we need to pick what kind of code we want to write in here. If we wanted to choose something else, we could click down here, Python or IronPython, but just C#. So once I click that, then this is going to pop up. I'm going to close it for now and just define the inputs. This we called vertices, and that's going to be a list of point3ds. So let's say list access type hint point3d. And in Rhino 8, it does treat lists a little bit different than in Rhino 7, or list access. It's an enumerable list. I think it's still that way anyways. So if I go in here, we have an list and not just a list. And so what I do a lot, if I just want to deal with a basic list, is I'll just convert all the incoming lists to lists. And in order to do that, we need to go up here and say using system.link, and then I'll save this and close out, and I'm just going to rename this to lowercase I, it doesn't really matter, I vertices. That way our variables can have the same name as it did when I wrote this one. You probably don't care if you just skipped ahead to the Rhino 8 part, but I'm going to say I vertices, and then here the first thing I'll do inside the scripting area is say var vertices equals I vertices dot toList. In our case here though, I don't even think this matters. We don't need to write system.link, and we don't need to convert this to a list. The iList is going to work just fine for us. But just in case you ever do need some functionality that comes with a list, and for some reason it's not working, go ahead and try to add system.link and convert it to a list, and that might solve your problem. So right now I'll show what the script looked like in the script editor for Rhino 7. You can see we have these gray areas in the Rhino 7 one. Those are gone in Rhino 8. It lets you edit everything. This is more what it would look like in a typical IDE, a programmer's development environment. The Rhino 7 version is a little more holding our hand, and in Rhino 8 they made a lot of improvements, so it's actually a lot easier to write code in Rhino 8. But it assumes you have a little more knowledge about coding, not that much more, but just a tiny bit more. It assumes you know that this is the area for all the global information, so this is where you write your additional code, your functions, classes, whatever, and everything inside the run script is what's going to be called every time the component is triggered, just like over here. This runs every time the component is called. So with that being said, we can go ahead and write this C# component. So in this video, we're just going to write one of the meshes. So I'll just go ahead and write one mesh here. And then in the next video, we'll fly through all of the other ones. We'll go very quickly through the other ones. So we don't need any additional code. Everything is going to be inside the run script function. The first thing we can do is declare our two data trees that we need. We need a data tree of meshes and a data tree of integers. The data tree of integers is going to be our Boolean pattern. Each mesh is going to have its own associated Boolean pattern. So let's make these data trees. The first one we can call mTree for mesh tree equals new data tree mesh. And then iTree for our integer tree equals new data tree. And then we'll say for each point 3D vertex in vertices. We're just going through all our vertices and putting them into the mesh, or putting them into a mesh, but I forgot to make that mesh first. So up here, let's make a new mesh, and we'll call this M0, mesh 0, equals a new mesh. Now we have an empty mesh called M0, and we can make a path for that mesh, gh path 0 equals new Grasshopper path, and it's just going to be designated as 0. And I forgot to capitalize this P. So back to our for each. For each of our vertices, we're going to add them to M0. .add or .vertices .add vertex. And our first face is just going to come from add face. Our first face is just going to come from the vertex 0 to vertex 8 to vertex 3. So if I make this a little smaller so we can see what vertexes those are. So we have going from 0 to 8 into 3. So counterclockwise like that. And then let's add this mesh to our tree. So we'll say mTree.add m0 at path 0. I'm going to save it and close this, and let's change the out. Let's see what this is saying. Let's see if it helps to plug this in. Okay, that's better. I'm going to change this just so we can match these. I'm going to change this to say mesh tree, and let's get another output, bool tree, or bool patterns, we'll say. I'm going to copy this, and then back inside here, instead of A, we're going to have bool patterns equals null for now, and mesh tree equals null for now. Actually, let's just put our mesh tree out and our iTree. So iTree is coming out of bool patterns, mTree is coming out of mesh tree. So we made the mesh, but we haven't made the pattern yet. The associated pattern for this mesh, save this and close this. So the associated pattern is going to be, this is going to be 0, this where there just coincidentally is a 0 here. This is a 0 value for this cube corner, and then all the other cube corners are going to be 1. So in the earlier version, when I recorded this, I made a separate path for the integer tree, but we don't need to do that. That's a step we can leave out here. So if you remember in the next video, when you're going through this, go ahead and leave that step out for each mesh. Just use the same path. So we're just going to grab this variable for the integer tree, or you can just skip ahead to the end where I show the code for all 14 meshes. But anyway, let's add all 8 integers to our integer tree. So in branch 0, we'll say I tree dot add, and then we said the first one is 0. So at index 0, we're adding 0, and then that's path 0. Then let's copy this first 3 more times, and then another 4 times. So the first one's 0, and the rest are 1. So our pattern is 0, 1, 1, 1, 1, 1, 1, 1. And we can add a couple slashes just to mark a separation between this and the next mesh to come. But again, for this video, we're just going to write this one mesh and see if it works. So I'll save it and close. Let's see if we have the correct pattern coming out. So at branch 0, we have 0 and then all 1s. And if we plug this into our mesh tree, looks like we have the correct mesh coming out. Okay, so that's it for this video. And in the next one, like I said, we're just going to make the next 13 meshes. We'll go much more quickly in that video though. So I'll see you there.